Reality isn't what we assume it to be. There are 30 paradoxes that can really shake how we see existence, and by the end, you might look at the world and yourself differently. Like, what if you went back in time and prevented your own birth? Or how a book could exist without an author? These aren't just stories. They're actual breaks in the universe's logic, found in black holes, or even in who you think you are. Each one opens up a deeper question. It makes you doubt the basics: time, space, your own mind. So what's real then? What do you actually believe? The Grandfather Paradox. It seems like a simple story, but it breaks a fundamental rule: cause and effect. You flip a switch, the light comes on. The cause comes first. That's the basic logic of everything. But traveling to the past turns that upside down. In the paradox, the effect you going back becomes the cause of its own erasure. You go back to do something that would prevent you from existing. Which means you couldn't have gone back to do it. It's a loop, a circle with no start and no end. So the paradox isn't really about the mechanics of a time machine. It's about causality. It shows that if you could go back, our whole understanding of how events connect would just break. One way to fix it is the idea of a self-healing timeline. Maybe anything you do in the past was always part of history. You were always there. Your attempt to change things is what created the present you know. That solves the paradox, but it introduces something else. It means your trip back, every choice you make, was predetermined. Your free will becomes an illusion. A story you tell yourself while following a script written by time. Another way out is the multiverse. When you go to the past, you don't change your own history. You branch off into a new, parallel universe. In that new timeline, you might never be born, but the original you from the original timeline still exists to have made the trip. This keeps the logic intact, but the cost is cosmic, an infinite splintering of realities with every decision ever made. The paradox forces a choice. Either our actions can create true logical impossibilities, which means this kind of travel can't exist, or our idea of free will is just a myth, or the universe is constantly dividing in ways we can never see. It asks what we value more, the consistency of reality or the freedom of our choices, and it suggests we might not be able to have both. That confrontation with beginnings leads to another puzzle. Even more profound, about the origin of everything from nothing. If cause and effect can break, then you have to ask where anything really starts. That brings in the Bootstrap Paradox. It's a time loop but personal. Think about a writer who can't write anything, stuck for years. Then a package shows up. Inside is a novel, a complete masterpiece with their name on it as the author, but it's dated 50 years in the future. So they copy it, they publish it word for word now, and it's huge. It defines a genre. Time goes by, the writer gets old, and they take that first printed copy, pack it up, and send it back. Back to their younger self. So the book exists, people read it, but who wrote it? Where did the story come from? The first sentence, the information, it doesn't have a source. It was never created, it was just transmitted. It pulled itself into existence like lifting yourself up, and it's not just a book, it could be a formula. A piece of music, an idea. The question is about where things come from. If time isn't a straight line, if the finished book can go back and cause itself to be written, then what's a first cause? Everything might just be a copy of a copy with no original. Some things might just be eternal, trapped in their own loop. Science fiction uses this, but it's a philosophical problem. It asks what authorship even means. Are our discoveries really ours, or are we just finding parts of a puzzle that was already finished? The Bootstrap Paradox doesn't need a first mover, a first thinker. It just needs a closed circle. A circle of cause and effect that's complete but mysterious. It makes you wonder if any idea is new, or if we're all just hearing echoes from a future that already knows us. and thinking about something creating itself that pushes you to the next edge. To the question of how you get something from nothing at all, the silence from the stars is just complete. It's a question that really started with a lunch conversation back in the 50s. Physicist Enrico Fermi looked at the numbers and he asked, "Where is everybody?" He wasn't joking. He was pointing out this staggering contradiction. The Milky Way has hundreds of billions of stars. So many of those stars have planets, and a lot of those solar systems are billions of years older than ours. If life is at all common, if intelligence emerges, then the math says the galaxy should be teeming. It should be full of radio signals, of engineering on a cosmic scale. We should see something, but we look up and we listened and all we find is quiet. That's the Fermi Paradox, the great silence, this contradiction between high probability and no evidence at all. But the paradox isn't just about aliens. It's a mirror. It forces these deep, sometimes unsettling questions about life and technology and survival. The proposed solutions, each one tells a different story about the universe and about us. There's one idea called the dark forest. It suggests the cosmos isn't a friendly place for a civilization that starts broadcasting. In a dark forest, if you make a sound, you reveal your location. You might be heard by something that sees you as a threat or as a resource. So the smartest strategy is to stay perfectly silent, to hide, to never announce you're there. In this view, the silence isn't empty, it's watchful. Every other civilization that made it this far learned the same lesson: be quiet or be removed. It's a chilling answer. It paints the universe as a place of permanent, profound caution. Then there's another idea, maybe even more sobering: the great filter. This theory says there's some immense, difficult barrier that stops life from advancing to the point where it fills the galaxy. This filter could be behind us. Maybe the jump from non-living chemistry to simple, replicating life is astronomically rare. We got lucky. If that's true, we might truly be alone, or the filter could be ahead of us. It could be a challenge so severe that no civilization has ever passed it. The development of advanced technology might inevitably lead to catastrophe. To a conflict or a collapse that a species can't survive. The silence, then, is a warning, a sign that the hard part isn't becoming a spacefaring civilization. It's surviving as one. There are other possibilities, less dramatic. Maybe intelligent life is common, but interstellar travel is physically impossible. The distances are just too vast to cross, or civilizations might rise and fall on timescales so short they almost never overlap. We could be like ships passing in an ocean of time, always missing each other by millennia. Or a truly advanced civilization might be so beyond our understanding that its presence is indistinguishable from nature. We wouldn't even know what to look for. The Fermi Paradox holds up a question we can't answer yet. Are we a miracle or a warning? Are we early to the party, or are we already in the quiet aftermath? That whole contemplation of cosmic scale and silence, it brings you back to another contradiction, one that comes not from the emptiness of space, but from the crushing density of a star's final act. The black hole's gravity doesn't just erase light, it erases reality. That's the black hole information paradox. It's a crisis in physics. To see why, you need two rules the universe is supposed to follow. The first rule is from quantum mechanics. Information is forever. Take a book burning to ash, it looks gone. But if you could track every particle of smoke, every bit of heat, every fragment, you could rebuild the book. The information is never destroyed, it gets scrambled. The past always leaves a trace. The second rule is from Einstein's general relativity. It says black holes have gravity so strong nothing escapes. Not even light. The boundary is the event horizon. Cross it and you're gone. Your information seemed deleted. For a long time, physicists thought these rules could coexist. The information was just trapped inside the black hole, hidden but preserved. Then Stephen Hawking found something. he showed black holes aren't completely black. Because of quantum effects at the horizon, they leak radiation, Hawking radiation. It's faint, but over eons, it makes the black hole lose mass, shrink, evaporate completely. And here's the problem. Hawking calculated this radiation is random, pure thermal noise. It carries no information about what fell in. No trace of the astronaut, the spaceship, the book. So follow it, an object falls in. The black hole evaporates. All that's left is this featureless radiation. Where did the information go? Quantum mechanics says it must still exist. Hawking's math says it's erased. That's the paradox. A fundamental law seems broken by the universe's own most extreme objects. The conflict is deep because it pits general relativity against quantum mechanics. They can't both be completely right here. Solving it means we're missing something deeper. Quantum gravity. One idea to fix it is the holographic principle. It suggests the information that falls in isn't stored in the interior volume. It's encoded on the two-dimensional surface, the event horizon. Like a cosmic hologram, the three-dimensional world inside could be a projection from that two-dimensional data. In that view, the information never actually falls in. It's smeared on the horizon, then slowly released in the Hawking radiation. The paradox makes us consider that space and time might not be fundamental. They might be emergent, like the wetness of water, coming from something more basic. If watching a black hole's fate challenges reality's fabric, then what happens when we turn that observation back on ourselves? If the deepest secrets of the universe depend on being seen, that tells us something about us. The observer's paradox. It takes quantum strangeness and makes it personal. There's a simple, baffling fact at the core. Looking at something changes what you see. It's not about being careful. It's a fundamental property at the smallest scale. A particle, an electron, it doesn't have a definite location until you measure it. It exists as a cloud of probabilities, a wave of potential. But the moment you set up a detector to find it, that wave collapses. The electron appears in one specific spot. The observation forced it to choose. It went from being everywhere at once to being right here. This leads to the most famous illustration. The one that's famously misunderstood, Schrödinger's cat. The thought experiment was meant to show how absurd it seems, applying quantum rules to everyday life. A cat in a sealed box, a device with a 50-50 chance of releasing poison. According to the theory, until someone opens the box and looks, the cat is in a superposition. Both alive and dead, only the act of observation resolves its fate. The paradox isn't about the cat, it's about the word observation. What does that mean? Where is the line? Is it the conscious awareness of a human? Is it the Geiger counter clicking inside the box? Or is it any interaction at all? A single photon bouncing off the apparatus? If consciousness is required, then reality is literally waiting for a mind to give it shape. The moon isn't there when you aren't looking. That idea is radical. It places us at the center of creation. It feels almost mystical, but if any interaction counts, then the universe is constantly observing itself, the cat's own presence. The air molecules in the box, these are all interactions that could collapse the state, so the world seems solid because it's always being measured by itself. This view removes the special role of the human mind, but it creates another puzzle. When exactly does a simple interaction become a definitive measurement? There's no clear threshold. The blurriness suggests something. It suggests our classical ideas of a separate, objective world are an illusion. Reality at its foundation is participatory. We are not just witnesses to the universe, we are collaborators in its unfolding. That shifts the ground. For centuries, science described a clockwork universe. It ticked along whether we watched it or not. The observer's paradox says that at the most basic level, that model breaks down. There is no detached, perfect view from nowhere. The act of asking a question changes the answer you receive. It challenges the very idea of objectivity. It suggests the crisp, definite world we experience is the end result of a process. Not the starting point, but if looking at the world changes it, then what is the world looking at when it looks at you? Identity feels solid. It feels like the ship of Theseus. An ancient vessel preserved as a monument. Over the years, its wooden planks rot. They're replaced one by one with new, identical pieces. After a century, every single original part is gone. Is it still the same ship? The city says yes. It has the same name, the same place of honor, the same continuous history. But then a collector gathers all the discarded original planks. She rebuilds the ship exactly as it was. Now there are two ships. Which one is the true ship of Theseus? The one with the continuous story, or the one with the original material? The paradox isn't about wood, it's about the thread of identity. What is the essence of a thing? Is it the physical stuff it's made of, or is it the form, the pattern, the story? We face a version of this every day. The cells in your body are constantly dying and being replaced. In about 7 years, nearly every atom that makes up you today will be gone, replaced by new ones from the air you breathe and the food you eat. Are you the same person you were 7 years ago? You feel like you are. Your memories, your personality, your sense of self, these patterns seem continuous. But the material is entirely new. This applies to everything. A river is never the same water twice, yet we call it by the same name. A flame burns, consuming its fuel, yet we see it as one continuous fire. We recognize identity not in static matter, but in dynamic persistence. The ship's identity might lie in its function, its designated role, or the collective agreement of the people who maintain it. The rebuilt ship, while materially original, has a broken story. It was a pile of scraps, then it was reassembled. Its history has a gap, but the thought experiment pushes further. What if you replaced the planks one at a time, but saved the old ones? And as you removed each old plank, you immediately used it to start building a second ship. At the end of the process, you have two complete ships at the same time. Which one left the harbor? The question becomes meaningless. It reveals that sameness is not a property of objects themselves, but a concept we use. A useful story we tell to navigate the world. When we turn this lens on ourselves, the ground shifts. You are a process, not a statue. A constantly changing pattern of information, carried by a constantly changing stream of matter. Your identity is the narrative you construct from your memories and experiences, held together by the feeling of a single, continuous perspective. The paradox asks what you are more attached to, the specific atoms or the ongoing story. And if it's the story, then how much can that story change before you become someone else? This isn't just philosophy. It touches on modern questions of teleportation, of digital consciousness, of what it means to survive over time. It suggests that the you that you know is a kind of elegant, persistent fiction, a necessary fiction that allows you to exist from one moment to the next. And if the self is this fluid, this dependent on a story we tell, then what about the story of everything that exists, the totality of all things, all stories, all identities? That leads to a paradox so vast it attempts to define existence itself. Absolute power, it always hits this one stubborn question. Could something all-powerful make a stone so heavy that it couldn't lift it? You have to follow it through. If the answer is yes, it can make that stone, then there's something it can't do. It can't lift the stone, so there's a limit. But if the answer is no, it can't make that stone, then there's also something it can't do. It can't create it. Either way, something is beyond its ability. The idea of unlimited power, it just collapses under its own weight. That's the Omnipotence Paradox, and it's not really about stones or lifting. It's about the boundaries of logic. Can logic even hold the idea of a being that operates outside all rules, even the rules of thought? The paradox says maybe it can't. that some ideas, when you push them to the absolute extreme, they become incoherent. They create a kind of short circuit in the mind. So one way people try to fix it is by redefining omnipotence. Maybe it doesn't mean being able to do anything imaginable. Just anything that's logically possible. Making a square circle is nonsense, it's not a real task. So maybe making an unliftable stone for an all-powerful being is also nonsense. A contradiction in terms, and so it's not a real limitation, but that it feels like moving the goalposts. It defines omnipotence in a way that automatically dodges the paradox. It says logic is the higher power. Even the divine has to obey the law of non-contradiction. A thing can't be both true and false at the same time. There's another approach, though. You can embrace the contradiction. Some philosophical and theological traditions say the ultimate nature of reality is beyond human logic. Our minds, built for a world of separate objects and linear time, they just can't frame the question right. The paradox in that view is a signpost, pointing to a mystery our tools are too blunt to solve. It shows the gap between our understanding and something truly infinite. And this struggle isn't just for theologians. You see it in our own world, whenever we try to conceive of true absolutes, a completely secure system that's also completely usable. Total personal freedom with perfect social harmony. These are modern versions of the same puzzle, goals that seem to undermine themselves the moment you try to define them perfectly. The Omnipotence Paradox, it teaches a humbling lesson. It suggests that logic might be the ultimate cage, not just for gods, but for every idea that tries to be everything at once. And if logic itself can be a constraint, then what happens when we turn logic against itself? To examine the very act of knowing, a judge tells a prisoner they'll be hanged at noon on some weekday next week. And it will be a surprise. The prisoner is alone in the cell, thinking it through. They realize it can't be Friday, because if they get to Friday morning and they're still alive, they'd know it has to be that day. So it wouldn't be a surprise, so Friday is out. But then, with Friday gone, they look at Thursday. If they reach Thursday morning and Friday is impossible, then Thursday becomes the last possible day. They'd expect it then, so that wouldn't be a surprise either. So Thursday is eliminated. They keep going like that. Wednesday goes, then Tuesday, then Monday. By pure logic, they conclude the hanging can't happen at all. It's impossible. They feel relief. But then, on Wednesday at noon, the executioner comes. And it is a complete surprise. Their flawless logic just failed. This isn't really about a clever judge. It's about what happens when you use logic to reason about your own future knowledge. The prisoner's deduction assumed their future self would be doing the same perfect reasoning, but the real world doesn't wait. The judge's statement created a loop. A statement about knowledge that changes the knowledge it describes. When the prisoner eliminated Friday, they changed the conditions. They made Thursday the new last day, which then became predictable, so they eliminated that too. Each step of the logic destroyed the surprise for the next day, but it didn't stop the event from happening on an earlier day. The surprise was preserved because the prisoner convinced themselves it was impossible. Their certainty was the trap. The paradox makes you ask where the reasoning broke. One answer is the judge's statement might be flawed from the start. It's a prediction that tries to control how it's received. It says you'll be surprised by X, but if you can deduce X, you won't be surprised, so the statement seems to undermine its own truth. It's like saying this sentence is false, a logical knot. Another view is the prisoner's reasoning has a hidden flaw. They assumed their future self would have perfect certainty. But in reality, on Thursday evening, would they be certain? Or would a tiny doubt remain? A doubt the judge is lying or a mistake could happen. That sliver of uncertainty is enough to preserve the surprise. The paradox requires perfect knowledge of your own future knowledge, which might be an illusion. You can't perfectly simulate your own future mind under that pressure. This touches things like game theory, the stock market. An investor who perfectly predicts a crash might act in a way that prevents it. A general who deduces the enemy's exact plan might cause the enemy to change it. When your reasoning is about a system that includes your own reasoning, you can't stand outside. You're part of the mechanism. The unexpected hanging shows logic turned inward can produce a kind of vertigo. Prediction isn't just calculating outcomes. It's navigating a loop where the prediction itself becomes a new factor, changing the landscape it tried to map. And that strange loop of language pointing at itself, that's exactly where the next paradox lies. A sentence can be a trap. There's a simple one: this sentence is false. It's a perfect snare. You think it through. If it's true, then what it says has to be correct, but it says it's false. So if it's true, it's false. That's impossible. So maybe it's false, but if it's false, then its claim that it's false isn't true. So it must be true, and you're back at the start. It's a dizzying loop. No exit. True becomes true again, forever. That's the liar paradox. It's ancient. A philosopher from Crete, Epimenides, said all cretins are liars. He was a cretin, so his statement condemned itself. If he's telling the truth, then he's a liar, so he must be lying. But if he's lying, then not all cretins are liars, so he could be telling the truth. Same loop. This isn't just a word game. It's a crack in the foundation of logic. It shows what happens when language turns back on itself, when a statement tries to say something about its own truth. For centuries, people tried to fix it. Maybe we should ban self-reference. Statements shouldn't be allowed to talk about themselves, but that's incredibly limiting. It would rule out things like, this sentence is written in English, or I am speaking now. The cure seems worse. The paradox's real power showed up in the early 20th century. Mathematicians were trying to build a perfect, complete system for all of mathematics. A set of rules so solid that every true statement could be proven, every false one disproven. No loose ends. Then a logician, Kurt Gödel, used a form of the liar paradox. He constructed a mathematical statement that essentially said, this statement cannot be proven within this system. Just like the liar, it created a loop. If you could prove it, you'd show it's false. If you could disprove it, you'd show it's true. Gödel showed that in any sufficiently complex logical system, there will always be true statements you cannot prove using the system's own rules. The system can never be both complete and consistent. It will always have blind spots, gaps it cannot fill on its own. That was a monumental shock. It meant absolute certainty, in mathematics or in any formal system of thought, is unattainable. There will always be truths that stand outside, just beyond the reach of proof. The liar paradox, a simple puzzle about words, pointed to a profound limitation at the heart of reason. It reminds us our tools for understanding the world, however sharp, have inherent boundaries. We build frameworks of logic to contain reality, but some truths spill over the edges. And if the very frameworks of our thought have limits, what about the framework of the cosmos itself? What are the boundaries of the universe? You look up on a clear night and you see stars against a dark sky. That darkness, though, it's a paradox. It's called Olbers Paradox. An astronomer in the 19th century asked the question, if the universe is infinite and static and filled with endless stars, then every line of sight from your eye should eventually hit a star. It's like standing in an endless forest. No matter where you look, you'll see a tree trunk, so the night sky shouldn't be dark. It should be a solid sheet of light, bright as the surface of the sun. Everywhere, but it's not. We see darkness with points of light. That contradiction meant something was wrong. The picture of a limitless, unchanging universe was wrong. Solving this paradox wasn't about a small tweak. It took a revolution. The answer comes in two parts. First, the universe isn't static, it's expanding. That expansion stretches space, and it stretches the light traveling through it. That stretching shifts the light toward red, making it dimmer. The farther away a galaxy is, the more its light is stretched and dimmed. Second, the universe has a finite age. Light travels fast, but it has a set speed. The universe is about 13.8 billion years old, so light from objects farther than 13.8 billion light years away hasn't had time to reach us yet. Our observable universe has a boundary in time, not space. We can't see beyond the distance light could travel since the beginning, so the dark sky isn't an empty void. It's a historical record. It tells us the cosmos had a beginning, a moment when the lights turned on. This solved paradox became a key clue for the Big Bang theory. A simple question, why is it dark at night, unraveled our assumptions and led to a new story of cosmic origins. And from that vast, expanding darkness, we're pulled to the opposite extreme. To a paradox that unfolds not across billions of light years, but inside a single, shrinking box. An observation can stop time, not as a metaphor, but literally in a quantum system. That's the quantum Zeno effect. It's named for an ancient Greek philosopher, Zeno, who had this paradox about an arrow in flight. He said at any instant, the arrow occupies one point in space. So how can it move? The modern version is just as strange. Take a radioactive atom. It's poised to decay. It has a probability to fall apart. But if you set up a detector to watch it, to measure it continuously, checking over and over whether it's decayed, something happens. The atom stays put. The constant observation suppresses its natural evolution. It's like the system, caught being looked at, can't get on with changing. That inverts our intuition about observation. We think measurement reveals a pre-existing state. You look at a clock to see the time, but in the quantum world, looking isn't passive. It's an intervention. Every time you check on that atom, you force it to reset its quantum clock. The wave function, which describes its probabilities, collapses back to the start with each measurement. If the checks are frequent enough, the system never gets the uninterrupted chance to transition. It's pinned in place by the observer's gaze. The paradox is deep. It suggests that at the foundation of reality, change isn't a given. It's a fragile process that needs privacy to unfold. Reality needs us to look away to do its work. And this isn't just about lab atoms. It hints at a deeper relationship between consciousness and the physical world. If continuous attention can halt a process, what does that say about the role of a conscious observer in shaping events? The effect has been shown in experiments, not with decay but with other quantum transitions like flipping a particle spin. The data is clear. Watch too closely and nothing happens. Stop watching and the world proceeds. It paints a picture of a universe that's fundamentally participatory, where the line between watching and doing blurs away. From this idea of freezing a moment through observation, we're pulled to a paradox that challenges the very river in which those moments flow. A message shows up before you've sent it. That's the tachyonic antitelephone. It's built on a hypothetical particle, the tachyon. In theory, tachyons always move faster than light. They're not slowed down by the universe's speed limit. They start beyond it, and if that existed, you could use it to send a signal, just a simple message. But relativity says if something moves faster than light, its timeline, from another observer's view, runs backward. It arrives before it left. That's where the paradox starts. You build the device, you get a message from your future self. It says, do not send the message. So you don't, but if you don't send it, how did you receive it? The information comes from nowhere, a closed loop with no origin. It's another Bootstrap Paradox, but this one comes from breaking the ultimate cosmic rule. This isn't just about a weird particle. It shows why physicists think the speed of light is more than a limit. It's a guardian of cause and effect. If you could send any information faster than light, you could arrange things so an effect comes before its cause. You could warn your past self about a mistake. Then you create a reality where the mistake never happens, which means the warning never had a reason to be sent. The logical structure of time unravels. The universe seems wired to prevent that. The math of relativity shows that as an object approaches light speed, its mass becomes infinite. It would take infinite energy to push it further. It's not just a barrier, it's a cosmic prohibition. The Tachyonic Antitelephone shows this prohibition isn't arbitrary. It's the foundation of a stable, coherent reality, where yesterday comes before today. It suggests the fabric of space-time is woven to preserve sequence, to keep the story of the universe moving in one direction. Without that safeguard, time would be a tangled knot of contradictions. And if breaking causality unravels time, then what about the opposite? What happens when you try to define the absence of everything? The very concept of nothingness leads to a paradox that's puzzled thinkers for millennia. The idea of nothingness, it sort of falls apart when you try to define it. But then you think about the things right in front of you, a pile of sand that seems solid. You can see it, but then you try to pin down what it is, and it just slips away. That's the paradox of the heap, the Sorites Paradox. You start with a heap of sand on a beach. You take away one grain, it's still a heap, obviously. Take another grain, still a heap. So you can make a rule. If something is a heap, removing one grain leaves a heap. That seems logical, but if you follow that rule grain by grain, you end up with one single grain. And by that rule, that one grain is still a heap, which is ridiculous. So the rule has to break somewhere, but where, which grain, when you remove it, turns the heap into not a heap? There isn't one. There's no clear line. The change is gradual, and our language doesn't have a sharp edge for it. This isn't really about sand. It's about the words we use, words like bold, or tall, or rich, middle-aged. They're vague, they have blurry edges. Take boldness. A man with a full head of hair, he's not bald. You pull out one hair. He's not bald, pull out another, still not. But if you keep going, one hair at a time, you get to a completely bald scalp. So when did he become bald? Which hair made the difference? The question doesn't have an answer. The concept doesn't give you one, and this vagueness creates a problem for logic. Our reasoning depends on clear categories. If A is true and A leads to B, then B should be true. But with the heap, you have a premise that seems true. Taking one grain leaves a heap, and if you apply it over and over, you get a false conclusion. The logic seems sound, but the result is nonsense. The paradox shows that classical logic, true or false, struggles with the real world, because the real world is full of gradients, spectrums. So how do we deal with that? One way is to accept that some statements aren't perfectly true or false. They're in between. That's fuzzy logic. It's used in computing for things like a thermostat deciding if a room is warm enough. Another view is that the problem is language itself. We made up the word heap to communicate, not to be philosophically precise. The boundary isn't in the sand, it's in our shared, rough agreement. We all kind of know what a heap is, and that's enough for everyday life. The paradox only really hits when you demand a precision that our ordinary language was never meant to have. It's a humbling thing to realize. So much of our shared reality is built on these soft categories. Our laws, social norms, even our identities, they often depend on thresholds that are inherently fuzzy. When does a drizzle become rain? When does an interest become a passion? The paradox of the heap tells us that looking for a single, definitive point is often the wrong question. The world isn't just black and white, it's filled with heaps of gray, and if our everyday categories are this vague, what happens when we apply our reasoning to the ultimate category, the infinite? A concept that, by its nature, defies all boundaries. Infinity isn't a large number, it's something else. To see that, you think about Hilbert's hotel. A hotel with infinite rooms numbered 1, 2, 3 forever, and on this night it's full. Every single room is taken, then a new guest shows up. In a normal hotel, you'd have to turn them away. But here, the manager has a way. She asks every guest to move. The person in room 1 goes to room 2. The guest in room 2 goes to room 3. Everyone moves from room N to room N+1. That frees up room 1. The new guest gets it. The hotel is still full. Now take it further. What if an infinite bus arrives? An infinite number of new guests, G1, G2, G3, and so on. That should be impossible, but the manager has another plan. She asks the current guests to move again. This time, the guest in room 1 goes to room 2. The guest in room 2 goes to room 4. Room 3 goes to room 6. Each guest moves to room number 2n. That leaves all the odd-numbered rooms empty. Rooms 1, 3, 5, and on. There are infinite odd rooms, so the infinite new guests from the bus can take those. The hotel was full, and then it took in another infinite crowd. This isn't just about rooms, it's about the arithmetic of infinities. With finite numbers, a full hotel can't take more. With infinite sets, you can. The set of natural numbers 1, 2, 3, 4 is the same size as the set of just the even numbers 2, 4, 6, 8. You can pair them 1 to 2, 2 to 4, 3 to 6. That's the property. A part can equal the whole. The hotel shows infinity plus 1 equals infinity, and infinity plus infinity still equals infinity. Our intuition is built for finite things. It breaks down here. This paradox is a way into that idea. It shows infinity isn't just a very big thing. It's a realm where normal addition doesn't work. Where the whole isn't greater than its parts. Logic can describe it, but we can't really picture it. And if the math of the infinite is that alien, it makes you wonder about our perspective. How do we, with our finite senses and short lives, make sense of a reality that contains something like that? The statistical argument is straightforward. And it's unsettling. If a civilization ever reaches a point where it can create vast simulations so complete they contain conscious beings who believe their world is real, then the numbers get very stark. If that's possible, and if that civilization runs even a modest number of these simulations, then the simulated minds would quickly outnumber the original, biological ones. You'd have one base reality and countless simulated ones. So if you are a conscious being, the odds are overwhelming that you are in a simulation. That's the simulation paradox. It's a modern take on an old philosophical fear. Think of Descartes, who wondered if an evil demon was deceiving his senses. Here, the demon isn't evil. It's a programmer, and the deception isn't malicious, it's just code. The paradox doesn't claim we are in a simulation. It says that if the premise is true, if such simulations are possible and likely to be created, then we probably are. It shifts the burden of proof. The extraordinary claim isn't that we're in a simulation. According to this logic, the extraordinary claim is that we're in the original reality. What would evidence even look like? Some point to potential glitches. Unexplained limits in physics, like the speed of light, could be processing constraints. The odd nature of quantum mechanics, the way it only renders detail when observed, might be a way to save computational power, but these are speculations. Not proof. The real power of the paradox is philosophical. It forces a confrontation with the nature of existence. If our reality is a construct, then physical laws aren't fundamental truths. They're rules programmed into the system. History isn't a record of actual events. It's a backstory seeded into the simulation at its start. Your memories, your sense of self, your entire lived experience, all of it could be a data stream. Convincing and complete, but no more authentic than a character's backstory in a video game. This doesn't render life meaningless. Even if our world is simulated, our experiences are real to us. Joy, connection, curiosity, hardship, they are the data of our consciousness. The paradox asks a deeper question about authenticity. What does real actually mean? If a simulated mind feels pain, is that pain less real? If it loves, is that love an illusion? The simulation paradox collapses that distinction. It suggests reality might be a matter of perspective, of information processing, not fundamental substance. Even numbers can be interesting. That's the idea. The interesting number paradox starts with this playful premise. It says every natural number is interesting. 1, 2, 3, all of them. The proof is a kind of trap. You assume the opposite. You assume there are boring numbers. Uninteresting ones. If that set exists, then there has to be a smallest one. The smallest uninteresting number. But then you look at that property. The smallest uninteresting number. That's a unique thing. It's noteworthy. So that number is interesting by definition. So it can't be in the set. You take it out. But then there's a new smallest uninteresting number. And the same logic applies. That one becomes interesting too. You can repeat this forever until the set is empty. So all numbers are interesting. It feels like a magic trick. A logical sleight of hand. It uses self-reference like the liar paradox, but it's gentler, more humorous. It isn't trying to break math. It's pointing at language. At a fuzzy boundary, what does interesting even mean? It's subjective. For a mathematician, a number is interesting because it's prime or a perfect square. Or the solution to an equation. For someone else, 7 is interesting because it's lucky. 13 is unlucky. 1024 is interesting because it's 2 to the 10th power. But is every number like that? The paradox suggests that if you look hard enough, any number can have a story, a reason to stand out. Even if the reason is just being the first number nobody found a reason for. The real lesson is about classification. Our minds love to categorize interesting versus uninteresting, significant versus mundane. The paradox shows these categories aren't fixed. They're imposed by us, and sometimes the act of trying to sort things, especially with a vague concept like interesting, creates a loop. The system trips over itself. From this playful dance with subjectivity, we are pulled to a choice of brutal logic, a choice that removes all personal feeling, and in doing so becomes a moral nightmare. A moral choice can become a single, brutal image. There's a runaway trolley on the tracks, heading straight for 5 people who can't move. You're standing by a lever. If you pull it, the trolley switches to a side track where it will kill 1 person. Do you pull it? That's the trolley problem. It's not a puzzle to solve. It's a spotlight on how our own conscience works. On the surface, the math is simple. 1 life against 5. A utilitarian calculation says you minimize harm. You pull the lever, 1 person dies to save 5. The greater good is served, but something deep in many people recoils. By pulling that lever, you're no longer a bystander. You become the active agent in that 1 person's death. Your hand does the deed. If you do nothing, you allow 5 to die, but you didn't directly cause it. That's the core conflict. It puts 2 ethical frameworks against each other. Utilitarian ethics, which judges actions by their outcomes, the greatest good for the greatest number. And deontological ethics, which judges actions by their nature, the idea that some acts, like killing an innocent person, are wrong in themselves, no matter the consequences. The problem strips away all context, no names, no histories, just numbers and a terrible choice. It shows our moral intuitions aren't a single, consistent voice. They're a chorus, often in disagreement. Psychologists have explored countless variations. What if the 1 person on the sidetrack is a child? What if the 5 are convicted criminals? What if, instead of a lever, you have to push a large man off a bridge to stop the trolley with his body? Most people who would pull the lever balk at physically pushing someone. That distinction is fascinating. It suggests that for many, direct personal force feels more morally significant than a mechanical, indirect action, even if the outcome is the same. The trolley problem continues to challenge far beyond philosophy. It's critical for the programmers of self-driving cars. How should an autonomous vehicle be programmed to react in an unavoidable crash? Should it swerve to hit 1 pedestrian to avoid 5? Should it prioritize its own passenger's life over others? These aren't abstract questions. They're engineering decisions that encode a specific moral calculus into a machine. The paradox shows that ethics, when forced into the clarity of an algorithm, exposes contradictions we often navigate with feeling, not logic. It teaches us that sometimes the hardest choices aren't between right and wrong, but between different kinds of right or different kinds of wrong. And it leaves us wondering if a truly moral decision can ever be made by calculation alone. This confrontation with an impossible choice about motion leads directly to a paradox about motion itself, one that seems to prove movement is nothing but an illusion. Motion can trap the mind. Zeno of Elea in ancient Greece had a paradox. It was about a race, a swift hero against a slow tortoise, and the tortoise gets a head start. For Achilles to pass it, he has to first get to where the tortoise started, but by the time he gets there, the tortoise has moved a little further, so then Achilles has to run to that new point. And again, when he arrives, the tortoise has crept forward again. This keeps happening. The race gets divided into an infinite series of steps, smaller and smaller steps. Achilles has to complete an infinite number of these tasks to pass the tortoise, and completing an infinite series seems impossible. So Zeno concluded Achilles could never overtake it. He'd be forever chasing, never catching. We know that's nonsense. The faster runner wins, but the logic seems flawless. It shows a confusion about how infinity relates to the physical world. The paradox assumes something. Because the journey can be described as an infinite number of steps, it must take an infinite amount of time, but that's the flaw. The steps are infinite in number, but they're also infinitely shrinking in the distance they cover and in the time they take. The time for each step gets smaller. Half a second, then a quarter, then an eighth, an infinite series of these shrinking time intervals. They can add up to a finite total. That total is the exact moment Achilles pulls even. And then, in the next instant, he speeds past. The tool that solves this is calculus, developed centuries later. It sums an infinite series, finds its limit. The paradox wasn't really about racing. It was a challenge to the idea of a continuum. Is space infinitely divisible? Can a finite length be made of an infinite number of points? Zeno's argument suggested if it is, then motion becomes impossible, because you'd have to traverse an infinity. The resolution shows our intuition about infinity is often wrong. The world is both continuous and traversable. An infinite number of moments can fit into a finite span. The finish line is reachable, even if the path has limitless divisions. This ancient riddle from a simple race forced a clearer understanding of motion, of time, and the mathematical fabric of reality. From this ancient puzzle about predicting a race's end, we jump to a modern dilemma. About predicting human behavior itself, a perfect prediction can feel like a cage. That's what the prediction paradox gets at. You have a super intelligent system. It analyzes everything, your brain chemistry, your habits, the weather, and it announces with certainty what you'll choose for breakfast tomorrow. You hear that. And now, in that moment, do you still have a choice? If you think you can do the opposite to prove the machine wrong, then its prediction wasn't perfect. It was fallible, but if the machine's prediction is truly 100% accurate, then your feeling of choice is an illusion. You were always going to pick that exact thing. The knowledge of the prediction becomes a new piece of data. It either changes the outcome or it confirms a path that was already set. This isn't just a futuristic puzzle. It's the latest version of an ancient debate. Philosophers and theologians have long wrestled with prophecy. If a divine being knows with absolute certainty what you'll do tomorrow, does that mean you aren't free? The technological version just replaces an omniscient being with an omniscient algorithm. The core conflict is the same. It's determinism against libertarian free will. Determinism says every event is causally determined by prior events. Libertarian free will says we are the ultimate originators of our own choices. The paradox shows a logical friction. Perfect foreknowledge and genuine, open-ended choice seem to cancel each other out. If the future is knowable in a specific, unchangeable way, then it's fixed. Our journey through it is just us discovering a script we had no hand in writing. On the other hand, if our choices are truly free and undetermined, then the future is inherently unknowable in its specifics. Any prediction is just a highly educated guess. One way out is to say the prediction could be so sophisticated it accounts for your reaction to it. The machine doesn't just predict your initial preference. It predicts you will hear the prediction, feel rebellious, and then choose the predicted item anyway, as a form of resigned acceptance. In this view, your defiance is part of the calculation. Your sense of freedom is just another variable in a vast, deterministic equation that preserves the accuracy of the prediction, but it makes freedom feel like a sophisticated puppet show. The prediction paradox forces an uncomfortable question about our own minds. Are we complex but predictable biological machines, or is there something about consciousness that introduces genuine novelty into the universe? It suggests that trying to know the future in perfect detail might be what destroys the possibility of the future being anything other than what we already see. From this conflict between knowledge and the self, we're pulled outward to a paradox of cosmic scale where the act of measurement confronts the limits of the measurable. The universe might have a pixel size. In physics, there's this thing called the Planck length. It's the smallest possible measurement of distance we can even conceive. It's incredibly tiny, about 1.6 times 10 to the negative 35 meters. To put that in perspective, if you enlarged an atom to the size of the observable universe, the Planck length would be about the height of a single tree. And it's not just a small number, it's thought to be a fundamental limit, a boundary where our classical ideas of space, of smooth and continuous space, they just break down. But then there's a paradox. How would you ever measure it? To see something that small, you need to probe it with something even smaller. You'd need a photon, a particle of light, with a wavelength shorter than the Planck length. But packing that much energy into such a tiny point creates an immense concentration of mass. According to general relativity, that concentration would be so dense it would instantly collapse into a microscopic black hole. The very act of trying to observe the smallest unit of space would destroy the experiment. It would swallow the probe and the information forever. So this suggests the Planck length isn't just a physical limit. It's an observational horizon, a point beyond which the concepts of here and there may cease to have any meaning. We can talk about distances smaller than this, but we could never interact with them, never measure them. The universe seems to have built a wall at the bottom of reality. And what lies beyond that wall? Some theories suggest space-time isn't smooth at these scales. It might be grainy or foamy, a seething quantum foam where tiny wormholes blink in and out of existence. In that view, the smooth continuum of space we experience is an illusion, like the smooth surface of a pond that's actually made of countless individual water molecules. The Planck length paradox teaches a humbling lesson. It shows that our ability to know the universe is constrained, not just by our technology, but by the laws of physics themselves. There may be layers of reality forever hidden from our view, not by distance, but by the fundamental rules that govern measurement and observation. If there is a smallest possible thing, then what about the opposite extreme? What happens when we contemplate the set of all things that are not part of themselves? In a cosmos that's eternal and chaotic, order is the ultimate statistical miracle. That's the Boltzmann brain paradox. It comes from the physicist Ludwig Boltzmann, who was trying to understand how our universe could have such low entropy, such high order, when everything tends toward disorder. If the universe is truly eternal and infinite, then every possible arrangement of particles will eventually happen by random chance. given enough time, a fully formed, conscious brain could just pop into existence from the void. Complete with false memories of an entire life, a coherent universe, and statistically, that isolated, momentary brain is far more probable than the gradual evolution of an entire ordered cosmos, one spanning billions of light years. So the paradox asks this question: why are you here, part of a vast, consistent universe with a deep history? Why aren't you just a lone brain that formed a second ago, hallucinating all of this? The math seems to say the hallucination is more likely. This isn't just a thought experiment, it's a direct challenge to certain cosmological models. If our theories predict a universe that lasts forever or cycles endlessly, then they also predict that Boltzmann brains should vastly outnumber ordinary observers like us. The fact that we don't seem to be Boltzmann brains is evidence against those models. It suggests our universe isn't infinitely old in a way that lets random fluctuations dominate. Or it points to special initial conditions at the Big Bang conditions that made our kind of ordered reality not just possible, but actually more probable than a sea of phantom minds. The paradox forces a choice. Either our understanding of cosmic probability is wrong, or the universe has a finite timeline, a unique beginning that prevents the statistical chaos from taking over. It's a profound argument from self-location. We use our own existence as data to rule out certain versions of reality. The very fact that we perceive a coherent, shared world is evidence against a cosmos drowning in temporary, solipsistic consciousness. From this dizzying prospect, a universe of hallucinated minds, we're pulled back to the mystery of the real, interconnected mind and the illusions it can create. A headache doesn't feel like a neuron firing. That's the hard problem. Science can map the brain in incredible detail. It can show you which parts are active when you see red or feel sad or remember something. It can describe the whole electrochemical process, but it can't explain why there's someone listening to that process, why there's an inner feeling at all. That gap between the objective process and the subjective reality, that's the hard problem of consciousness. It's a paradox because science has done so well explaining everything else from the outside. A planet's orbit, electricity, cell division, those are mechanisms. But the taste of chocolate, the sting of embarrassment, just knowing you're reading these words, those are from the inside. They only exist from the inside, and no description of brain activity, no matter how detailed, seems to close that gap. It's like having a perfect breakdown of a movie projector, frame by frame, but no way to explain the story on the screen. One idea is that consciousness isn't a product of complex computation. It's a fundamental part of reality, like space or time or mass. That view is often called panpsychism. Some basic form of experience is in all matter. A human brain's complex consciousness comes from organizing those basic conscious pieces in a special way. It's a radical idea. It means the universe isn't dead, silent stuff. It's inherently experiential. The other possibility is that our science is incomplete. We're using tools made to study an objective world, but consciousness is the lens we use to see that world. We're trying to look at our own eyeball with that same eyeball. Some argue we might need a new kind of science, one that can formally include first-person data, the raw data of experience itself. This paradox is at the center of our own existence. It asks what it means to be you. Are you just a biological machine, or is there something irreducibly private and immediate about your awareness? The hard problem suggests the greatest mystery might not be in the distant cosmos. It might be right here behind your own eyes, and if our own perception is such a deep puzzle, it makes you question how reliable perception even is. You open your eyes for the first time. Light and color come in, just a blur of shapes. Someone puts two objects in front of you, a cube and a sphere. You've known these shapes your whole life, but only by touch. You've felt the edges, the smooth curves, now you see them. Can you look and say which is which? That's the Molyneux problem. It gets at how we know anything. The philosopher William Molyneux asked John Locke this in the 17th century. He wasn't just asking about blind people, he was asking about the mind's architecture. Are the ideas from one sense, like touch, automatically linked to ideas from another, like sight? Or is that a connection we have to learn? Do we have to build a bridge between two separate worlds of data? The intuitive answer might be yes. A sphere is roundness, a cube is squareness. That essence should carry over, but the problem points to something deeper. The tactile feeling of roundness, the even pressure on your palm, is a completely different kind of information than the visual pattern of a circle. The play of light and shadow, a curved line against a background. Your brain gets two different codes without a lifetime of practice linking what something looks like to what it feels like. Those codes might be unreadable. The knowledge is there, but it's locked in the wrong language. Modern medicine has given us a kind of answer. There have been cases where people blind from birth had their sight restored by surgery. The result wasn't sudden, miraculous clarity. The world was first an overwhelming confusion of visual noise. They could see lines and colors, but they couldn't recognize objects. They couldn't navigate a room. A flight of stairs was a terrifying puzzle of light and dark patches. They had to learn to see painstakingly over months and years. And in those early moments, they couldn't reliably match a cube they saw to a cube they felt. The senses were islands, not yet connected by the bridges of experience. This shows a truth about perception. We don't just receive reality, we construct it. The brain isn't a passive camera or a microphone, it's an active interpreter. It takes raw, senseless data from the eyes, the ears, the skin, and weaves it into the coherent, three-dimensional world we experience. That weaving is a learned skill. The Molyneux problem shows that our seamless reality is a masterpiece of neural integration, built over a lifetime. What we take for granted as simple recognition is actually an astonishing feat of computation and connection. It makes you wonder how many separate realities we live in. The world of sound, the world of sight, the world of touch, each is its own domain. And the unified experience we call being here is the brain's brilliant, learned synthesis. This paradox of the senses forces us to see the fragile, constructed nature of our own perception. And if the categories we use to perceive the world are learned, what about the categories we use to define the world itself? What happens when we try to put everything into neat, logical boxes? A simple question can break logic. Think of a library, but this library doesn't have books. It has lists. There's a list for all novels, a list for all biographies. Then there's a different kind of list, a list that doesn't contain its own title. The novel list doesn't have novels on it, so it goes into that new collection. The list of lists, though, it does include its own title, so it stays out. Now you make a master list of all the lists that don't include themselves. Call it list R, and here's the question. Should list R include itself? If it does include itself, then by its own rule, it has to be a list that doesn't include itself. So it shouldn't be there, but if it doesn't include itself, then it fits the criteria. It is a list that doesn't include itself, so it has to be added. Either way you answer, it flips to the opposite. That's Russell's paradox brought out of set theory. Bertrand Russell wasn't playing with words. He was looking at the building blocks of mathematics, which are built on sets, collections of objects. He asked about the set of all sets that are not members of themselves. The same impossible loop showed up. If it is a member of itself, it can't be. If it isn't, it must be. For mathematicians at the start of the 20th century, this was a catastrophe. They were trying to base all of mathematics on pure, flawless logic. Russell's simple question showed a crack in that foundation, a crack from self-reference. The system let sets be defined in ways that talked about themselves, and that self-inclusion led to contradiction. The paradox couldn't be ignored. It meant naive set theory, the intuitive version, was inconsistent. A logical system with a contradiction can be used to prove anything, true or false. It becomes meaningless. Fixing this required new rules. Mathematicians like Ernst Zermelo and Abraham Frenkel built axiomatic set theory. They made careful axioms, starting principles, that explicitly stopped a set from being a member of itself. They built walls to block that kind of dangerous self-reference. The solution was elegant, but there was a cost. It showed that our most secure fortress of truth, mathematics, rests on rules we choose to avoid paradox, not on some inevitable, perfect bedrock. Russell's paradox teaches a humbling lesson. Even in the pure realm of abstract thought, where we feel safest, paradox can come out of the shadows. It shows that consistency often means limiting our own freedom, putting up signs that say, "No entry" on certain paths of thought. And if the rules of our most logical systems need guardrails to prevent collapse, what does that say about the unwritten rules that hold a society together? A society that never says no can destroy itself. That's the paradox of tolerance. Karl Popper, the philosopher, he framed it as a practical defense for an open society. He argued that unlimited tolerance would be exploited. The people preaching intolerance, they would use that society's freedoms to dismantle the system protecting them. They'd use free speech to end free speech, use democratic processes to end democracy. So to preserve a tolerant society, Popper said, we must be intolerant of intolerance. We must refuse to extend the full protections to those whose goal is to destroy it, and that's where the paradox lies. The principle seems to eat its own tail. To protect tolerance, you sometimes have to act in a way that seems intolerant. It feels like a contradiction, a logical knot, but it's a question of boundaries. Where does a society draw the line? What speech, what actions cross over from dissent into an active threat to the framework that allows dissent in the first place? This isn't an abstract puzzle. It's a daily challenge for any nation built on liberal ideals. It forces a choice between pure principle and necessary pragmatism. If you hold free speech as absolute, you might allow a movement to grow, a movement that will later silence everyone else. But if you start restricting speech, who decides what's too intolerant? That power can be misused. It can slide into censorship, into silencing merely unpopular ideas. The paradox forces a society to constantly examine its own foundations. It asks what the core, non-negotiable values really are. Usually that core includes equality before the law, the right to physical safety, the integrity of democratic institutions. Intolerance here isn't just holding a prejudiced view, it's actively working to strip those rights from others. The paradox teaches that tolerance is not passive. It's not indifference, it's an active commitment to a set of rules, rules that allow difference to exist, and like any set of rules, it requires enforcement to be meaningful. That enforcement means sometimes saying no. This creates a fragile, necessary balance. A society must be open enough to allow criticism and change, but firm enough to protect the space where that criticism can happen. It's a social contract that must defend itself. The paradox of tolerance shows that some ideals can't survive in their purest, most absolute form. They require wisdom, judgment, and sometimes a painful, paradoxical defense. From this delicate social contract, we return to a fundamental cosmic contract, one about the nature of information itself. A billiard ball can create its own past. Joseph Polchinski, a physicist, gave us this mechanical riddle. It's stripped of human choice. You imagine a simple setup. A wormhole, a tunnel through space-time. You throw a billiard ball at its opening. The wormhole sends the ball back in time, just a few seconds. It comes out of a second opening, on a path that intersects its own younger self. The older ball strikes the younger one. It knocks it off course. The younger ball veers away now, missing the wormhole entirely. but if it never goes in, then the older ball that just hit it could never have come out. So there's no collision, which means the younger ball goes in after all, and it creates the older ball that stops it. It's a perfect physical contradiction. A deterministic machine that runs itself into a logical wall. This is Polchinski's paradox, sometimes called the billiard ball paradox. Its power is in the simplicity. It removes the human element, no assassin, no choice, just a ball, a wormhole, and the laws of motion. It shows the grandfather paradox isn't about free will. It's about consistency. Even in a clockwork universe, time travel introduces loops that can't be resolved. The physics seems to demand two contradictory histories. One where the ball goes in, and one where it doesn't. Both can't be true. So how could the universe allow time travel without breaking? One answer is the Novikov self-consistency principle. Proposed by physicist Igor Novikov, it states that any actions taken by a time traveler were always part of history. The only possible events are those that are self-consistent. There are no paradoxes because paradoxes are physically impossible. In the billiard ball scenario, this principle would force a single timeline, a consistent one. Perhaps the older ball emerges and only gives the younger ball a glancing blow, just enough to alter its path slightly, but not enough to stop it from entering. The younger ball goes in, becomes the older ball, and emerges to deliver that exact same glancing blow. The loop is closed, the history is stable, nothing changes because it always happened that way. This idea is profound. It suggests that if time travel is possible, the universe is a master editor. It allows only those plots that make sense, no contradictions. Only consistent loops. Your attempt to change the past is what always created the present you know. Your freedom is an illusion within a predetermined, self-healing story. Polchinski's ball, bouncing in a closed curve of cause and effect, shows time not as a river flowing one way, but as a Möbius strip, a single surface where past and future are linked. From this vision of a cosmos that edits itself into consistency, we turn to a paradox born from the opposite, a world of utterly inconsistent, yet equally valid descriptions. Justice can be a perfect trap. There's a story from ancient Greece. A student named Euothlus wanted to study law under the sophist Protagoras. They made a deal. The student would pay his fees only after he won his first court case. It seemed straightforward, a fair arrangement, but then the student delayed. He didn't take any cases. Protagoras got tired of waiting. He decided to sue for the payment, and in the courtroom the trap snapped shut. The student, defending himself, made his argument. "If I win this case today," he said, "then the court's ruling says I don't have to pay. But if I lose this case, then by our original contract, I still haven't won my first case. So I don't have to pay. Either way, I owe nothing." It was a perfect legal defense built from the very agreement that bound them. Protagoras was ready. He presented the mirror image. "If you lose this case," he argued, "then the court orders you to pay me. But if you win this case, then you've just won your first case. Therefore, by our contract, you now must pay me. Either way, you owe the fee." Both arguments are logically sound. Each follows from an accepted premise, the court's authority and the contract's condition. Yet they point to opposite verdicts, mutually exclusive. The judge is paralyzed. Granting victory to one side validates the other's claim. It's a closed loop of reason. The paradox isn't about who is right. It's about what happens when two valid systems of rules collide. Contract law and judicial verdict. They collide in a self-referential circle. Each system uses the other to justify itself. That creates a deadlock. There's no external exit. This ancient drama reveals a fragility in our structures of justice and agreement. We build systems on logic. We expect them to produce clear answers. But when those systems fold back on themselves when they judge the very conditions that created them, they can short-circuit. The truth becomes not a point to discover, but a loop to be trapped within. It asks where final authority truly resides, when reason contradicts itself. From this legal impasse where human judgment meets its limit, we are lifted to another impasse, a final, cosmic one that asks not about laws in a courtroom, but about the fundamental laws of existence. The universe ends in a frozen silence. That's the heat death. It comes from the second law of thermodynamics. Everything runs on differences, hot and cold, order and disorder. These differences are gradients. They let work happen, but entropy always increases, disorder always grows. Over eons, all gradients smooth out. The cosmos reaches a uniform temperature. Lukewarm, no stars burn, no planets orbit, no reactions occur. It's a static sea, particles drifting apart in expanding darkness. In that state, no work is possible. No structure, no life, no thought, no consciousness. It's the end of all process, and that's where the paradox starts. If the final state makes observers impossible, what does that state mean? Who is it for? A sunset needs someone to see it. A story needs a mind to reach its end. The heat death is the cosmos' story, written in physics. But if the conclusion guarantees no one will read it, no awareness that the last page turned, then does that conclusion have any reality? It's a question about existence and observation. If a tree falls with no one to hear, we debate the sound. But if a universe dies with no witness, can we say it had an ending? Does end require a perspective? This challenges the arrow of time. The flow from past to future, from low entropy to high, gives our lives direction. We remember the past because we are low entropy systems in a universe still rich with gradients. But at heat death, time as a measure of change may cease. Without processes, there are no clocks. The universe is an eternal, featureless now. So the paradox asks if time is an emergent property. It only exists because things happen. At the end, when nothing happens, does time still pass, or does it stop like a frozen frame? The heat death is ultimate solitude, a cosmos that spent billions of years birthing stars and life, only to become a place where no memory remains. It renders all struggle, all beauty, transient. Yet the paradox offers a strange comfort. The fact we are here asking this question proves the universe is not in that state. We live in the brief epoch where gradients are still steep, where light exists, where minds can ponder the coming darkness. Our consciousness is a flicker in the cosmic night. But it's a flicker that illuminates the whole story. The heat death is inevitable, but our witness to the journey isn't an accident. It's part of the physics that allows the question to be asked. From this final silence, we're pulled to a paradox about a very specific and very loud end. 23 people in a room, that's enough. The odds are better than 50-50 that two of them have the same birthday. That's the birthday paradox. It feels wrong. Your intuition says you'd need a lot more because there are 365 days in a year. So 23 people, that's just a tiny slice of the calendar. But the trick isn't about one person matching another specific person. It's about all the possible pairs. With 23 people, you can make 253 different pairings, and each one of those pairs has a chance to match. The probability doesn't grow in a straight line. It explodes. By the time you have 57 people, the chance is over 99%. It's almost a certainty. Our brains are built for linear thinking. For direct cause and effect, we're not wired to get this kind of combinatorial explosion. We underestimate how fast connections multiply. This paradox shows up in a lot of places. In cryptography, it predicts when you'll find a password collision. In data analysis, it explains why seemingly rare coincidences are actually common in big datasets. It's a humbling lesson about chance. The universe isn't trying to be surprising. It's just following the math. our surprise is a measure of our own blind spots. We see a shared birthday as a meaningful sign, a strange connection, but in a room of strangers, it's not strange, it's statistically normal. The birthday paradox connects the abstract world of probability to daily life. It explains why you might meet someone with your same rare name, why you keep seeing the same number sequence. Our minds are pattern-seeking engines. They want to find stories in the noise. This paradox reminds us that sometimes the most compelling stories are just probability doing its work. It prepares us to question not just coincidences, but the whole framework. The framework where all coincidence, all logic, and all reality might be contained. Every paradox we've looked at seems to point in the same direction. The last one isn't really a new puzzle. It's more like the ground all the others stand on, the paradox of reality. After going through 29 of these contradictions in time, logic, how we see things, you come to this one possibility. That trying to build a complete, consistent, objective picture of the world is itself a paradoxical task. It's like a mapmaker's problem. A map is supposed to represent a territory. But to be perfectly accurate, a map of a forest would have to show every leaf, every insect, every shadow that moves. That map would have to be as large and as complex as the forest itself. And then it would have to include itself, a map within the map forever. So the perfect representation becomes impossible. It either simplifies and leaves things out, or it tries to be complete and gets tangled in itself. Our models of reality face that same trap. We've seen it everywhere. Gödel showed that any logical system rich enough will contain truths it can't prove. The system is either incomplete or it breaks. Quantum mechanics tells us we can't observe the world without changing it. The observer is woven into what we see. And the hard problem of consciousness, it suggests the thing experiencing reality, the subjective feeling of being, stays outside any objective physical description we could build. These aren't just separate mysteries, they're symptoms, signs that our tools, logic, measurement, even our own consciousness, are part of the system they're trying to describe. We're not gods looking down on a clockwork universe from outside. We're cogs in that clockwork, trying to understand the whole machine while being turned by its gears. Any model we build will have the fingerprints of the modeler. It will either leave something out, or it will contain the paradox of including itself. This doesn't mean reality is illogical. It suggests something more. That reality operates on a logic deeper and more expansive than the true or false framework our minds are built for. Our perception, our math, our science, they're brilliant adaptations. They're tuned for survival in a middle-sized world of objects and causes. But when we push them to the extremes, to the beginning of time, to the edge of a black hole, to the nature of our own awareness, they strain. They show their seams. The paradox of reality is the ultimate humbling. It's recognizing that the universe may not be built to be fully comprehensible to the minds it has produced. The quest for a single, neat, contradiction-free theory of everything might be a beautiful, necessary, impossible dream. Not because we aren't smart enough, but because understanding is a dialogue, not a monologue. We're in conversation with a cosmos that's stranger than our languages can ever fully say. So after climbing this mountain of paradoxes, what does it mean? It means the contradictions aren't walls, they're windows. Each one, from the grandfather's impossible fate to the silent heat death, is a crack in the facade of our assumptions. Through those cracks we catch glimpses of something vaster, a reality that's not less than logical but more. A reality that includes the loop, the observer, the grain of ambiguity, the unresolved question as features of its design. This journey through 30 ideas doesn't end with an answer. It ends with a deeper kind of wonder. Grasping reality isn't a fist closing around a truth. It's an open hand feeling the shape of the mystery. And in that openness, in dwelling in the question, we might find the closest thing to understanding we'll ever know. That mirror is shattered, and the reflection it gives back is us. These 30 paradoxes, these elegant traps of logic and perception, they aren't roadblocks. They are the path. Each one is a signpost at the very edge of a map. It marks the territory where our current models of thought just give out. The contradiction we hit isn't a flaw in the universe's design. It's a flaw in our own vision, a signal that we need to look again with new eyes. Think of them as catalysts. The grandfather paradox didn't end time travel stories. It forced physicists to explore self-consistent timelines, to explore the multiverse. The Fermi Paradox's great silence isn't an answer, it's a generator. A generator of 100 profound questions about life, about technology, about survival. The black hole information paradox isn't a dead end, it's the engine. The engine driving our search for a theory of quantum gravity. These puzzles are the growing pains of a species learning to think bigger. They are the universe's way of saying your current toolbox is insufficient. For this job, build a new one. What emerges from this journey is a portrait of reality, and it's breathtakingly strange. A reality where time may not flow in one direction. Where observation creates the observed, where the self is a story told by changing atoms, where the entire cosmos might be one possibility in an infinite sea of others. This isn't the neat, mechanical clockwork of earlier centuries. It's something far more dynamic, more participatory, more mysterious. Our everyday world of solid objects and predictable cause and effect. It's not an illusion. But it is a special case, a quiet backwater in a much wilder ocean. And so the ultimate lesson is one of profound humility. To stand before these ideas is to realize our most basic assumptions are provisional. About time, about space, about identity, about truth. They are the best stories we have told so far. The paradox teaches us to hold them lightly, to cherish curiosity over certainty. The most dangerous thought is not "I do not know," it is "I already know." These logical knots exist to untie that certainty, to open the mind back up to wonder. As we integrate these glimpses, we are not left with a set of answers. We are left with a richer set of questions, a deeper set of questions, and perhaps that is the point. The journey through paradox prepares us not for a final destination of knowledge, but for a permanent state of exploration. It equips us with the intellectual courage to question everything, especially the ground we think we stand on. For in that questioning, in that willingness to dwell in the mystery, we engage with the cosmos in its truest form. In its most astonishing form, these intellectual earthquakes, they don't just shake things, they reshape the whole landscape. Every paradox, whether it's a time traveler caught in a loop or the universe cooling into silence, it's like a tremor. It shows a crack in what we assumed was solid ground, and after that shaking stops, the world looks different. You realize these aren't just puzzles to be solved and put away. They're permanent, they're part of the terrain, they're like signposts but written in a language of contradiction, pointing toward truths that are just too big or too strange for our ordinary logic. It teaches you something, it humbles you. The universe runs on its own principles. It doesn't have to make sense to us. It doesn't have to feel comfortable. Our brains, they evolved for specific things, to spot danger, to find food, to navigate each other. They're magnificent tools, but they're tools for a certain scale, for a certain kind of problem. When we point them at the fundamental nature of everything, at the infinite or the infinitely small, at the origin of it all, it's no wonder they sometimes short-circuit. The paradox, that's the sound of the short circuit, that's the spark in the dark, but in that moment of confusion, something happens. Our understanding actually grows. We have to invent new math like calculus to deal with Zeno's race. We're forced to imagine new physics like quantum gravity for a black hole's paradox. We're pushed to question our own consciousness, our own identity. Wrestling with these contradictions, it isn't a failure, it's the engine, it's how discovery works. It's how we grow, so take that sense of wonder with you. Next time you look up at the dark between stars, or even just pause over a simple choice, remember this. Remember that the solid world around you, the steady flow of time, the feeling of being yourself, these are probably just the surface. The reality underneath is far more mysterious, more connected, more astonishing.